Welcome to the Sleepy Astronomer, where we drift through the mysteries of the universe, one sleepy story at a time. Tonight, we're diving into one of the most mind-bending questions in modern astrophysics. What would happen if you fell into a wormhole? But before we begin our journey across space and time, take a moment to get cozy, let your body relax, and let me know, where in the world are you watching from tonight? Wherever you are, I'm glad you're here. Now, let's begin. Imagine you're lying under a dark, open sky. The stars above twinkle softly, scattered across the endless canvas of the universe. You begin to wonder about the strange and hidden pathways that might exist out there, secret tunnels through space and time. And then the word appears in your mind, like a whisper from some distant galaxy. Wormhole. But what exactly is a wormhole? At first glance, the term sounds like something out of a science fiction novel, and in many ways it is. Yet it's also rooted in the real mathematics of modern physics. A wormhole is, in theory, a tunnel or passage through the fabric of space and time itself. If space were like a sheet of paper, flat and seemingly unbroken, then a wormhole would be like folding that paper in half and punching a hole straight through, connecting two distant points instantly, not by travelling across the surface, but by taking a shortcut through the mysterious folds of reality. To understand a wormhole, we need to step back for a moment and consider what space and time actually are. According to Einstein's theory of general relativity, space and time are not separate things. Instead, they form a unified, dynamic fabric, space-time, that can bend, twist and stretch in response to matter and energy. Massive objects like stars and planets curve this fabric, and that curvature is what we experience as gravity. Now imagine a region of space so intensely curved that it doesn't just dip like a bowl, but actually connects to a different part of the universe, or perhaps even a different universe entirely. This idea, proposed by physicists Albert Einstein and Nathan Rosen in 1935, gave birth to what's now known as an Einstein-Rosen bridge. And that's the technical name for what we casually call a wormhole. The name wormhole itself was actually popularised later by physicist John Wheeler. He asked his students to picture a worm crawling through an apple. The worm could either walk across the apple's curved surface, along a journey, or tunnel through the core, taking a much faster path. That tunnel, he said, was like a wormhole in space-time. But the deeper you dive into the concept, the more bizarre it becomes. For one, wormholes are not like regular tunnels with walls and ceilings. They are purely theoretical structures, solutions to Einstein's equations, and may not exist at all. No one has ever seen a wormhole, not even with the most powerful telescopes. If they do exist, they may be hiding somewhere far beyond our reach, or possibly existing only for the briefest moments before collapsing. Some wormholes are thought to connect different points in space. Others might link entirely different times, allowing for the mind-bending possibility of time travel. Still others could be portals to parallel universes, places where the laws of physics themselves may be slightly or completely off focus. But there's a problem. Most natural wormholes, if they exist, are believed to be unstable. They would collapse before anything, or anyone, could travel through. The gravitational forces inside them would be so extreme that even light might not survive the journey. For a wormhole to remain open, it would need something that defies all our current understanding. a substance with negative energy, often called exotic matter. This isn't regular matter, like the kind your body is made of. It's a theoretical material that could push space-time apart instead of pulling it together. If such a thing exists, and we're not sure it does, it might hold the key to keeping a wormhole stable and traversable. But even if we had the technology to create or stabilize one, wormholes would raise countless other questions. Could we navigate them safely? Where would we end up? Could we return? And perhaps most haunting of all, would we be the first ones to ever go through? Or might someone or something be waiting on the other side? As you continue to rest, your mind gently floats among the stars, tracing the silent arcs of galaxies and pondering the hidden passages that might lie in the shadows between them. Somewhere, in the deep silence of space, a wormhole may be waiting. Or perhaps it already passed through you without a sound. And in that calm, lingering thought, you feel the gentle tug of curiosity, the kind that doesn't demand an answer right away. It simply invites you to wonder and drift a little deeper into the great unknown. To truly understand how wormholes emerged from the landscape of physics, we must travel back in time, back to the early 20th century, when a young Albert Einstein was beginning to reimagine the universe itself. Before Einstein, people thought of space as a fixed, empty stage upon which the drama of the cosmos unfolded. Gravity, according to Newton, was simply a force that pulled one object toward another, like the Earth pulling on the moon, or an apple falling to the ground. But Einstein saw something deeper. He proposed that gravity wasn't a force at all, but rather a consequence of how mass bends the fabric of space and time. In 1915, Einstein unveiled his theory of general relativity, a revolutionary framework that changed how we think about the universe. In his new model, massive objects like stars and planets create curves in the four-dimensional fabric of space-time. Imagine a heavy ball placed on a rubber sheet. The surface bends under its weight. If you then roll a smaller ball nearby, it follows a curved path, not because there's a force pulling it, but because the space it moves through is bent. This was gravity, as Einstein understood it. His equations describe this curvature with extraordinary precision. But like all great theories, general relativity also raised new questions. What happens at the very limits of space and time? What lies at the edges of black holes, where the curvature becomes infinite? And could space-time be shaped in such a way that two distant points are joined by a shortcut? In 1935, Einstein partnered with another physicist, Nathan Rosen. Together they explored a curious solution hidden within Einstein's own equations. What they discovered wasn't a new force or particle, but a bridge, a kind of tunnel that seemed to link two distant regions of space. This hypothetical structure became known as an Einstein-Rosen bridge. Their solution described two black holes connected by a throat or tunnel, a mathematical structure that was smooth and symmetrical, but it wasn't stable. According to their calculations, this bridge would pinch off the moment anything tried to pass through it. It was like a soap bubble that popped as soon as it formed. Fascinating but ultimately unreachable. Still, the idea planted a seed. Other physicists began to wonder, what if there were a way to keep the tunnel open? Could this bridge, this strange mathematical curiosity be transformed into a real traversable wormhole? But even as Einstein and Rosen published their work, they were cautious. Einstein, in particular, disliked the more speculative or fantastical implications of his own theory. He didn't believe wormholes could actually exist in the physical world. To him, the bridge was a useful abstraction, one that helped explore questions about quantum particles, not cosmic travel. In fact, their original paper wasn't even about space travel or wormholes at all. It was a proposal to describe particles like electrons without singularities, or infinite densities. Yet their bridge, a subtle wrinkle in the fabric of the cosmos, refused to vanish from the minds of scientists and dreamers alike. Decades later, in the 1950s and beyond, physicists began returning to this idea with fresh eyes. John Wheeler, one of the most influential figures in modern theoretical physics, was captivated by the strange landscapes predicted by general relativity. He gave the concept of the Einstein-Rosen bridge a more poetic and accessible name, the wormhole. It helped people visualize the idea, like a tunnel through an apple, or a passage through folded paper. Wheeler also introduced the concept of quantum foam, the idea that at the tiniest scales, space-time might be frothing with microscopic wormholes, flickering in and out of existence. Though we can't observe them, these tiny fluctuations might be essential to the universe's underlying structure. Meanwhile, Kip Thorne and his colleagues took the question even further. In 1988, they published a paper outlining how a stable, traversable wormhole might exist, if exotic matter with negative energy density could be used to hold it open. This exotic matter isn't like anything we find in everyday life. It's hypothetical, and it may or may not be possible. But the math works. And the implications? They're staggering. If such a wormhole could be created, it might allow for travel between distant galaxies, or even between different points in time. Suddenly, what had begun as a mathematical curiosity in Einstein's equations was blossoming into a full-fledged scientific mystery, with tendrils reaching into quantum mechanics, cosmology, and even philosophy. Of course, we still don't know if wormholes exist. They remain theoretical, beautiful, haunting solutions to equations that describe a universe far more flexible and mysterious than we ever imagined. But the fact that these strange structures naturally emerge from Einstein's work is a kind of poetry in itself. It suggests that the universe might be more interconnected than it seems, that the vast distances between stars could be bridged not by brute force or impossible speeds, but by gentle folds in space-time, hidden in plain sight. And so, as you lie back and drift deeper into thought, you can imagine Einstein at his desk, scribbling on a chalkboard late into the night, drawing curves and loops, unknowingly opening the door to one of the greatest what-ifs in the history of science. The equations hum quietly in the background, like a lullaby for the curious mind, whispering secrets of tunnels, bridges, and passages through the unknown. Let's begin with something simple, something familiar. Picture a flat sheet of paper. Imagine you place a tiny black dot on one edge and a red dot on the opposite side. These two dots are far apart, maybe inches, maybe miles, depending on the scale. In our everyday understanding of space, to get from the black dot to the red one, you would have to draw a line between them, the long way across the page. That's how we usually move through space, one step at a time, from here to there, across the fabric of reality. But what if, instead of crossing the page, you simply folded it so the two dots touched? Now the distance between them is zero, just one step, one breath, one blink. That's the essence of a wormhole. This simple visualization, a folded piece of paper, is often used to explain a deeply complex concept: how space-time, the very structure of our universe, could theoretically bend in on itself to create a shortcut. What we perceive as vast, uncrossable distances between stars and galaxies might not be so vast at all if space could fold, warp, or tunnel in ways we can't yet access. In Einstein's theory of general relativity, space is not rigid. It is flexible. It's like an enormous, invisible sheet stretched across the cosmos. Mass and energy cause it to curve, and objects move along these curves. That's why planets orbit stars, not because they're being pulled by an invisible hand, but because the stars bend space around them, and the planets are simply following the curves of that bend. But space isn't just curved around stars. In theory, under the right conditions, space could be folded so drastically that two separate points, possibly light years apart, become directly connected. The folds aren't just metaphors. They're built into the math of the universe itself. This brings us to the idea of dimensions. We live in 3 dimensions of space and 1 of time. But what if space-time has more dimensions than we can perceive? Imagine a 2-dimensional being living on the surface of a sheet of paper. That being could only move forward, backward, left or right, but never up. Now imagine you, a 3-dimensional creature, punching a hole through the paper. To the 2-dimensional being, it might seem like magic, an impossible leap between 2 points. But to you, it's just a shortcut, a wormhole. In our 3-dimensional world, a wormhole might be a tunnel not just through space, but through space-time. That means it could, in principle, allow for instantaneous travel, not only between distant places in the universe, but also between different times. And that idea brings with it both fascination and discomfort. The very structure of reality could be navigable, folded, crossed. Of course, folding space is not something we can do yet, not with rockets or technology or even our best theories. It remains, for now, in the realm of possibility rather than practicality. But the concept isn't just fantasy. It emerges naturally from the mathematics of Einstein's field equations. These equations describe how mass and energy shape space-time. And under certain extreme conditions, those equations allow for the formation of a tunnel, a bridge, between 2 separate regions. Some scientists even believe that if wormholes exist, they may have formed naturally in the early universe, when space-time was still expanding rapidly and fluctuating wildly. Perhaps, for the briefest moment, space folded in on itself, and 2 distant places were connected. Maybe some of those wormholes still exist, hiding out in the vastness of intergalactic space, invisible and silent. To make one stable, though, we would need something extraordinary, exotic matter. This strange substance would have negative energy density, unlike any material we know. Its purpose? To keep the tunnel from collapsing, to hold the walls of the wormhole open like the beams of a bridge. Without exotic matter, the wormhole would close too quickly for anything to pass through. With it, maybe, just maybe, a traveller could make the journey. And what would that journey feel like? No one can say for certain. Some models suggest you wouldn't see anything unusual until the moment you entered. Then the universe would twist and ripple around you. Stars might blur. Time might stretch. Gravity could shift, flowing in strange directions. And then, suddenly you might find yourself somewhere new. A different star system, a new corner of the galaxy, or even another universe entirely. But there are risks, enormous ones. If the wormhole isn't stable, it could collapse mid-journey, trapping you in an eternal void or crushing you under impossible gravitational forces. Radiation, turbulence, time dilation, these are more than sci-fi buzzwords. They are real possibilities in a universe as complex and powerful as ours. Still, the idea lingers, because to fold space, to leap across the stars in a single moment, is a dream that speaks to something deep within us. It whispers of freedom, of escape, of transcendence. And even if we never build a wormhole ourselves, understanding them helps us see our universe not as a static box, but as a living, breathing, ever-shifting tapestry. You can almost feel it now, as you close your eyes. The folds of space drifting softly like the fabric of a curtain in the wind. A gentle ripple across the cosmos. A quiet possibility just waiting to be discovered. And in that stillness, in that vast and timeless calm, the universe feels just a little closer, a little softer, a little more like home. If wormholes are real, where are they? This question lingers on the edge of imagination and scientific curiosity. We've spoken about what wormholes are, hypothetical tunnels through the very fabric of space and time. But in a universe as vast and mysterious as ours, why haven't we seen one? Where might they be hiding? And how would we even begin to look for them? The search for wormholes is unlike the search for stars or planets. Wormholes, if they exist, would not emit light like a sun, nor reflect it like a moon. They might not have a visible surface at all. Instead, they could resemble black holes, regions of space where gravity is so intense that nothing, not even light, can escape. And that's where the confusion begins. Because some theories suggest that certain wormholes might actually look just like black holes from the outside. Black holes are already strange enough. They warp space and time, trap light, and have mysterious boundaries called event horizons. If a wormhole had a similar outer appearance, we might already be looking at one without knowing it. Imagine peering through a telescope at a seemingly ordinary black hole, dark, heavy, silent. You see stars swirling around it, pulled by its immense gravity. But hidden behind that veil of darkness, just beyond the event horizon, could be the mouth of a wormhole. A tunnel not into oblivion, but into another part of the universe. So how would we tell the difference? Some physicists propose that the gravitational footprint of a wormhole might be slightly different from a traditional black hole. For example, the way light bends around it, a phenomenon called gravitational lensing, might be unusual. In 2019, when astronomers captured the first image of a black hole's shadow using the Event Horizon Telescope, they opened the door to a new kind of observation. If we ever detect a black hole that has lensing patterns or radiation signatures that don't match expectations, it might suggest something stranger is going on. Another possibility lies in the behaviour of matter near the event horizon. In a normal black hole, material spirals inward and disappears, but in a wormhole, matter might behave differently. Some theories suggest that material could disappear into the wormhole's mouth and reappear elsewhere. If we ever observe matter vanishing from one region of space and reappearing in another, perhaps even with identical properties, it could be a sign that a wormhole is at work. But even that is speculation. One of the biggest challenges is that wormholes, if they exist, could be extremely unstable. They might flicker into existence for just a fraction of a second before collapsing again. This would make them nearly impossible to detect with current technology. The universe may be filled with microscopic wormholes, remnants from the birth of the cosmos, that are far too small and brief to be seen. There's also the question of location. If wormholes exist naturally, they might be rare, very rare. Perhaps they are hidden in the dark regions between galaxies, far beyond where our telescopes can currently reach. Or perhaps they are nestled within black holes themselves, their mouths concealed behind the veil of infinite gravity. Alternatively, wormholes might not exist at all until someone, or something, creates them. Some scientists speculate that advanced civilizations, if they exist, might have the technology to create and stabilize wormholes using exotic matter or energy. If that's true, a wormhole might not be something we stumble upon by accident. It might be something designed, built, with intention. Like a cosmic doorway placed in deep space, invisible to us unless we know exactly how to look. There's also a speculative but tantalizing idea that certain phenomena we already observe might be explained by hidden wormholes. For example, fast radio bursts, sudden, high-energy signals from space that last just milliseconds, still puzzle astronomers. Could they be the signature of information or energy passing through a wormhole? We don't know, but the more we study these mysteries, the more we begin to wonder. There's even a thought, shared by some theoretical physicists, that the very structure of space-time at the smallest scale might be riddled with tiny fluctuating wormholes, part of what's sometimes called quantum foam. These would be far too small to travel through, but they might play a role in how the universe behaves at the quantum level. In this view, wormholes aren't just rare oddities. They're everywhere, part of the background hum of existence. And yet, despite all these possibilities, no confirmed wormhole has ever been observed, not one. For now, they remain purely theoretical, beautiful, elegant solutions to complex equations dancing just beyond the edge of our vision. But that's the nature of exploration. The first exoplanet was only discovered in 1992. Before that, many believed planets outside our solar system were simply too distant, too dim, too impossible to find. Today, we've found thousands. The same may one day be true for wormholes. Perhaps the tools we need are not yet invented. Perhaps we're not even asking the right questions. Still, the universe is vast. Trillions of galaxies, endless stars, countless secrets. And somewhere, drifting silently through the cold reaches of intergalactic space, could be a doorway, invisible, waiting, silent. And perhaps one day, when our instruments are precise enough, or our understanding deep enough, we will see something, not a star, Not a planet, but an opening. A soft distortion in space. A place where the stars don't quite behave the way they should. A whisper in the fabric of reality. The mouth of a wormhole. And with that discovery, everything would change. So let's imagine for a moment that a wormhole exists somewhere out there in the vastness of space. Maybe it's hidden near a black hole. Maybe it's floating silently between galaxies. You somehow discover it, this swirling, tunnel-like passage through space-time, and, drawn by the thrill of discovery and the promise of instant cosmic travel, you move toward it. But before you even get close enough to touch its edge, something happens. The entire structure shudders, ripples, and then collapses, gone, as if it had never been there. This is not just the stuff of science fiction. It's one of the most sobering truths in the theoretical physics of wormholes. The vast majority of them, if they exist at all, would be catastrophically unstable. To understand why, we need to return to the foundations of Einstein's general relativity. Wormholes arise naturally from his equations. They're not imaginary or fanciful. They're embedded in the mathematics of curved spacetime. But while the equations allow for these tunnel-like solutions, they don't guarantee that those tunnels will stay open. In fact, they strongly suggest the opposite. Left to the forces of nature alone, a wormhole would be a fleeting thing, unstable, fragile, and almost immediately doomed to collapse. Think of it like blowing a soap bubble. You might be able to create a shimmering, spherical membrane for a few seconds. It glistens in the sunlight, a perfect little world. But almost as soon as it forms, it begins to tremble and quiver. The slightest disturbance, a breeze, a bit of dust, even gravity itself causes it to pop. The same is thought to be true of wormholes. In the vacuum of space, under the relentless tug of gravity and the pressures of the surrounding universe, most wormholes would pinch shut before anything could pass through. This collapse isn't gentle. In many models, the wormhole throat, the narrowest part of the tunnel, shrinks rapidly to nothing, squeezing space and time together in an instant. Anything caught inside would be crushed by gravitational forces far stronger than those near a black hole. You wouldn't be transported. You wouldn't be sent somewhere else. You would simply cease to exist in any meaningful way. And the danger begins even before you enter. As you approach the wormhole, the intense warping of space-time could stretch and distort your body. This effect, known as spaghettification, occurs near black holes and could happen near unstable wormholes as well. Different parts of your body would experience different gravitational pulls, your feet being drawn in faster than your head, or vice versa, pulling you apart like strands of spaghetti. Even if, somehow, you managed to reach the edge of the wormhole unharmed, there would be another problem: feedback. Wormholes are thought to allow not just matter, but also light and radiation to pass through. In a stable wormhole, this isn't a problem, but in an unstable one, light can begin to reflect back and forth inside the tunnel. Just as sound can echo in a cave, light and energy could bounce between the two mouths of the wormhole, building up rapidly. This feedback loop creates a runaway effect, flooding the wormhole with energy until it tears itself apart. Some models suggest that this collapse would happen faster than the speed of light could carry a signal across it. That means even if you entered the wormhole with a plan, sending a probe, measuring the space, calculating trajectories, you wouldn't have time to react. The collapse would be over before your sensors knew it had begun. There's also the issue of tidal forces. These are the same kinds of gravitational gradients that stretch and squeeze objects near massive celestial bodies. In an unstable wormhole, these tidal forces could become so extreme that even atomic structures would be torn apart. It wouldn't just be dangerous, it would be utterly unsurvivable, even for machines. And yet, despite all this danger, wormholes still tempt us. Why? Because in theory, they offer something nothing else in the universe does: instantaneous travel across immense distances. The temptation is strong. If only we could stabilize the tunnel, protect it from collapse, reinforce it against gravitational collapse and quantum fluctuations, we might be able to use it. But this is where nature demands a toll. To keep a wormhole open, we would need something strange, something outside our ordinary experience. Physicists call it exotic matter. This matter would have negative energy density. Not negative like a debt or deficit in human terms, but negative in the sense that it would push against gravity rather than pulling. Regular matter, like stars, planets and people, warp space-time by drawing it inward. Exotic matter, on the other hand, would push space-time outward, counteracting the collapse of the tunnel. We don't know if exotic matter exists. Some quantum theories suggest that small amounts might appear briefly in vacuum fluctuations, the tiny random pops of energy that occur even in empty space. But we've never captured it, never controlled it. And we certainly don't have enough to weave the structure of a stable, traversable wormhole. In the absence of exotic matter, we are left with fragile, flickering structures, brief tunnels that form and collapse so quickly that they are effectively useless for travel. Dangerous mirages in the deep. This doesn't mean wormholes are impossible. It just means that the universe, as we know it, doesn't make it easy. The laws of physics might allow these tunnels, but they don't seem to favour them. Like secret doors in an ancient castle, they may exist, but they are locked tightly, with keys made of theories we haven't yet discovered. And so we look up at the stars and dream of bridges between galaxies, shortcuts through space-time, corridors into the unknown. But we also know deep down that if such paths exist, they are not for the reckless. They are dangerous, unforgiving. Most wormholes are instantly deadly, not because the universe is cruel, but because it is precise, balanced, and filled with mysteries that do not reveal themselves easily. Still, we wonder, and we wait. In the silent darkness between the stars, where gravity bends the light and time itself seems to stretch and ripple, lies a tantalizing possibility, a stable wormhole, a tunnel through space and time that doesn't collapse, a bridge between two distant parts of the universe, or perhaps two different universes entirely, that remains open, waiting to be crossed. But to make such a marvel possible, nature demands something extraordinary, something beyond what we've ever held in our hands or seen in the lab. It demands exotic matter. Exotic matter is not just a fancy name for something rare. It refers to a very specific and very strange kind of material. Matter that possesses negative energy density. This means, in a sense, that it behaves in the exact opposite way of everything we know. Regular matter, like the earth beneath your feet or the stars above your head, has positive energy. It pulls. It attracts. It curves space-time inward like a heavy ball on a trampoline. But exotic matter does something radical. It pushes. It repels. It bends space-time in the opposite direction, creating a sort of anti-gravity effect. And that effect is exactly what a stable wormhole would need. Because wormholes, by their nature, want to collapse. The pressure of space-time, the gravitational pull of the surrounding universe, the very shape of the tunnel itself, these forces all work to close the passage. They try to squeeze the wormhole shut the moment it forms. To hold it open, something must push back. This is where exotic matter comes in. Imagine a tunnel through a mountain. To keep it from collapsing, you line the inside with steel beams. In the case of a wormhole, those beams aren't made of metal. They're made of negative energy. An invisible scaffolding that braces the throat of the wormhole against the crushing weight of space-time itself. But does exotic matter actually exist? That's where things become even more mysterious. In classical physics, negative energy seems impossible. Everything we encounter in daily life has positive mass and energy. We can't touch something and find it weighs less than nothing. But in the strange world of quantum physics, negative energy might just be real, at least in tiny temporary amounts. One of the best known examples comes from the Casimir effect, a phenomenon predicted in 1948 by Dutch physicist Hendrik Casimir. In a vacuum, what we might think of as empty space, quantum fields still flicker and dance with virtual particles popping in and out of existence. Place two metal plates extremely close together, just a few nanometers apart, and something strange happens. The vacuum between them has less energy than the vacuum outside. This creates a tiny force that pushes the plates together. In effect, a region of space is created that has lower than normal energy, what some interpret as a negative energy density. It's not exotic matter in the form you'd need for a wormhole, but it's a tantalizing hint. A whisper from the quantum realm that negative energy is not just fantasy, it's real, but only in small, delicate, short-lived ways. Another potential source of negative energy comes from certain quantum field theories that allow for violations of classical energy conditions, the rules that usually prevent things like wormholes and warp drives from being possible. These violations, however, are still deeply theoretical. They live in equations, not in test tubes. And yet, despite all the obstacles, the idea persists. Some physicists have imagined using hypothetical particles or fields, like tachyons, which travel faster than light, or phantom energy, which could accelerate the expansion of the universe, to generate exotic matter. Others have speculated that stable wormholes might already exist in nature, stabilized by forms of exotic matter we simply haven't discovered yet. Perhaps they're relics from the birth of the universe, left behind in the chaotic moments after the Big Bang. Perhaps they float silently in the deep voids between galaxies, their entrances cloaked by darkness and time. In the 1980s, physicist Kip Thorne and his colleagues explored this idea in more detail, laying out the mathematics of traversable wormholes. They showed that, in theory, such a wormhole could be kept open if you had enough exotic matter. It wouldn't require an infinite amount, but it would need to be arranged precisely delicately, like a cosmic balancing act. They even worked on these ideas partly to address questions raised by science fiction, specifically Carl Sagan's novel Contact, which featured a wormhole-based journey across the stars. Sagan wanted the story to be grounded in science, and Thorne helped make sure it was. But here's the catch. Even if exotic matter exists, we have no way to produce it in large quantities. We don't know how to shape it, how to store it, or how to prevent it from vanishing. It's like having the blueprint to build a magnificent ship, but no access to the rare material the hull requires. We can dream, we can calculate, we can theorize, but until we learn how to harness negative energy, stable wormholes remain out of reach. And yet, the dream remains, because exotic matter, strange as it sounds, offers a loophole in the laws of nature, a way around the limits that space and time impose, a whisper of hope that one day we might not need to cross galaxies one star at a time, but instead step through a doorway and arrive somewhere new. There is poetry in the possibility that something as alien and elusive as negative energy might one day be the key to crossing the cosmos. That buried in the wild equations of quantum theory, there lies a path, not just through space but through understanding. And so, we search, we theorize, we listen to the silence between the stars, wondering if a wormhole has already opened and closed without a sound, waiting for the day we unlock the secret of exotic matter, not as a fantasy, but as a bridge to the impossible. Until then, the universe holds its breath, and so do we. Imagine for a moment that the impossible has become possible. Somewhere deep in space, drifting in the silence between galaxies, a wormhole has opened. And not just any wormhole, but a stable one. Scientists have somehow managed to hold it open with exotic matter, defying the collapsing pressures of space and time. Instruments have confirmed it. The math checks out. The tunnel remains still, humming faintly with the energy of the cosmos. And now, you're standing at its edge. What would it feel like to enter? This is a question few have dared to answer, not because it lacks intrigue, but because it teeters on the edge of imagination. What happens when a human body, a fragile, living system designed for Earth, encounters something that violates the ordinary rules of the universe? As you float toward the mouth of the wormhole, you might first notice the light. Light behaves differently near intense gravitational fields, and a wormhole would be no exception. The stars behind it could appear stretched, distorted into rings or arcs, gravitational lensing at its most extreme. This visual warping might make the entrance look like a shimmering sphere or an inky void surrounded by a halo of bent starlight. Not dark, not bright, but something else entirely. A presence in space, more felt than seen. Approaching it, time begins to act strangely. From the outside, observers might see you slow down. To them, it could appear as though you're frozen, hovering just at the edge of the wormhole's mouth, never quite entering. But from your perspective, nothing changes. Time continues to flow smoothly. You pass the threshold. And then, everything shifts. The moment you enter a wormhole, you leave behind the familiar framework of space and time. The inside of a wormhole is not like the inside of a tunnel. It's not lined with stone or metal, not a tube you can walk through. It's a region where geometry bends in ways our minds were never meant to grasp. Distances may become meaningless. You could travel millions of light years in the span of a few seconds. Not by accelerating, not by moving through space, but by stepping across it, as if folding the universe like paper and slipping through the crease. What would you see? No one knows for sure, but theories suggest you might encounter a corridor of strange light, a twisting shaft of colour and motion where the usual laws of physics break down. Imagine being suspended in a realm where every direction feels like down, where gravity has no centre, and where space is constantly folding and unfolding around you. Time might feel stretched or compressed. Seconds might feel like hours, or perhaps hours would vanish into nothing at all. Your body, shielded from the violent forces by protective technology, perhaps wrapped in fields of stabilized exotic matter, might not feel any motion at all. There would be no wind, no sound, no vibration, just a strange, profound silence, like floating in the deep ocean with no shore in sight. And then, without warning, the tunnel ends. But this is not where you began. You emerge in a completely different region of the universe. The stars are unfamiliar. The constellations don't match any chart you've ever seen. Perhaps you're near the centre of a distant galaxy, where stars burn blue and fast. Or maybe you're adrift in a quiet corner of intergalactic space, where galaxies are just faint smudges on the black velvet sky. Time too may have shifted. Depending on how the wormhole is aligned, you might have travelled not just across space, but across time. It could be years ahead or behind your original moment of departure. To you, the journey was instantaneous, but on Earth, entire generations may have passed. Or perhaps you've arrived in the past, at a moment before your journey began, triggering paradoxes the universe isn't quite prepared to resolve. But let's return to the moment of entry. Psychologically, what would it be like? No human mind is equipped to perceive four-dimensional curvature. Our brains evolved to walk on solid ground, to navigate forests and rivers, not to comprehend non-Euclidean geometry. Inside a wormhole, your visual and spatial senses might become overwhelmed. You could see versions of yourself ahead and behind, stretched like reflections in a hall of mirrors. You might feel motion without movement, or stillness that vibrates, colours without names, sounds that don't correspond to any vibration of air, but echo somewhere deep inside your perception of time. And yet, there is something comforting about the idea that a human consciousness could survive such a voyage. That we could enter the deep structure of the universe, navigate its hidden corridors, and return, transformed not just physically, but spiritually. Because falling into a wormhole, if such a thing could happen safely, would not just be an act of travel, it would be an act of transcendence. You would become a voyager between realms, someone who had stepped outside the limits of light and distance, who had touched the deeper architecture of the cosmos, and returned with stories no one else could tell. And perhaps the most mysterious part of the experience would be how natural it feels. After all, space-time is the foundation of everything we are. We are made of atoms forged in stars, governed by the forces of gravity and quantum uncertainty. Entering a wormhole might not feel like leaving reality, it might feel like returning to its source. So as you drift back from this thought experiment, resting safely under your blanket or curled in your favourite chair, imagine for a moment that the universe is not as vast and disconnected as it seems. That somewhere in the folds of space-time, doorways exist, and that one day you might find yourself standing at the threshold and stepping through, not into destruction, not into chaos, but into wonder. As you journey deeper into the wormhole, something extraordinary begins to happen, not just to your location in space, but to your very experience of reality. The rules you've always relied on begin to dissolve. Light bends in impossible directions. Time pulses like a living thing. Reality itself seems to twist and shimmer. You are no longer simply moving from point A to point B. You are falling into a place where the ordinary concepts of direction, motion, and distance start to unravel. What you're experiencing is not just a passage through space, but a profound distortion of light, time, and perception. From the moment you cross the threshold into the wormhole, your senses are bombarded with phenomena you've never encountered. The very fabric of space-time is no longer smooth and predictable. Instead, it ripples and twists like a river of mercury, flowing in all directions at once. Light, which usually travels in straight lines, now bends and curves around you, looping and stretching as if unsure of where it's supposed to go. Beams of starlight may seem to spiral endlessly, or pass by you, circle around, and pass again from a different direction. This is not just an optical illusion, it's the result of intense gravitational lensing. In a wormhole, the curvature of space-time is so extreme that it redirects the paths of photons, those tiny packets of light, causing them to follow strange, looping trajectories. You might see your own back in front of you. You might see distant galaxies warped into glowing rings, or multiple images of the same star appearing from different angles. The universe folds around you like a kaleidoscope, every moment presenting a new and alien vision. But it's not just light that changes. Time begins to act in ways that defy your intuition. Under normal circumstances, time flows in one direction, forward, and at a relatively steady pace. But inside a wormhole, time itself is stretched, compressed, twisted. The closer you get to the wormhole's throat, the narrowest, most concentrated part of the tunnel, the more intense these distortions become. Depending on how the wormhole is structured, time could speed up for you while standing still for an outside observer, or the reverse could happen. You might experience only a second while days, years, or centuries pass elsewhere. This phenomenon is known as time dilation, and it's a well-documented consequence of Einstein's theory of relativity. We see hints of it near black holes, where gravity is strong enough to slow the passage of time. In a wormhole, this effect could be magnified to unimaginable degrees. You could exit the wormhole to find yourself in the distant future, or even the distant past, depending on how time has flowed differently on either side. And all the while, your experience of space is transforming too. The wormhole doesn't take you on a path through ordinary space. It connects two distant regions by collapsing the distance between them. It's not unlike being in a house where the hallway between two rooms vanishes, and you step from one into the other instantly, as if the walls themselves had reshaped to accommodate your movement. The space between stars becomes meaningless. You are no longer subject to the cosmic speed limit, the speed of light, because you are not moving through space at all. You are moving with space, through a tunnel that simply skips the in-between. But these distortions come at a price. Your internal clock may no longer match the external world. If you left Earth at midnight and returned a few seconds later, you might find that centuries have passed. Or you might arrive back before you left, creating paradoxes that challenge our understanding of causality. Could you change the past? Or would the universe, in its infinite complexity, always course correct? Some physicists speculate that wormholes, if traversable, would require careful tuning of time and space to prevent such paradoxes. Others believe that time loops could be self-consistent, that any action you take in the past was always part of history, and nothing can be truly changed. These are not just philosophical questions. They emerge directly from the math that governs the universe. As you continue through the wormhole, you may begin to lose your usual sense of direction. The traditional axes, up, down, left, right, begin to merge. You might feel as if you're being stretched without feeling any pain, or compressed without being crushed. Some parts of your body may experience different gravitational forces than others, and without sophisticated shielding, this could be dangerous. But assuming perfect protection, the effect is more surreal than painful. It's as if your body has become part of the geometry itself, flowing through the tunnel as naturally as a river through a canyon. You may also begin to feel time emotionally, not as a ticking clock, but as a presence, an atmosphere. The past may feel physically near, hovering just behind your shoulder. The future may press against you, rushing toward you like a current. The wormhole blurs the lines between what has happened and what will happen. In this place, cause and effect can dance in strange and unexpected ways. And then perhaps most surprisingly, the universe begins to quiet. The distortions settle, the tunnel widens, the light begins to return to something familiar. The swirling geometry around you untangles, and the space ahead begins to look, if not normal, then at least comprehensible. The journey through the wormhole is nearly over. As you approach the exit, you may notice that time begins to normalize. Light straightens, gravity relaxes, your body adjusts as though waking from a dream. And when you emerge, the universe greets you anew. But something is different. Something has changed. Not just in the stars around you, but in you. Because to fall into a wormhole and survive its distortions of light and time is not just a journey through physics. It is a journey through perception, through understanding. You've touched the edges of reality's deepest structure. You've seen time stretch and space fold. You've felt the universe breathe. And when you look up at the stars again, they will never seem so far. Nor will they seem unreachable. They will feel, somehow, like home. There's something undeniably magical about the idea of moving faster than light. For as long as humans have gazed up at the stars, we've dreamed of breaking that barrier, of soaring across the galaxy in the blink of an eye, defying the cosmic speed limit that binds us to our little corner of the universe. Light, after all, moves at nearly 300,000 kilometers per second. It takes light over 4 years just to reach the closest star to Earth. To travel even a fraction of that distance would take us generations using conventional spacecraft. But what if there were a way to cheat the system? That's where wormholes come in. These theoretical passages through space-time don't just offer an exciting vision of the universe. They offer a potential workaround to the universal limit imposed by the speed of light. But here's the twist. Wormholes don't actually allow you to travel faster than light in the traditional sense. What they do is far stranger. They reshape the path itself. To understand this, imagine two distant points in the universe. Let's call them A and B. If you were to travel from A to B in a straight line through regular space, even at the speed of light, the journey might take thousands or millions of years. But a wormhole, if one connects those points, offers a shortcut. Not because you move faster than light, but because the distance you have to travel becomes incredibly small. Instead of journeying across the surface of space, you cut through the depths of it. It's like standing on a vast sheet of fabric. Walking across the fabric to a point on the far side takes time. But fold the sheet so that the 2 points touch, and suddenly you can step from one side to the other instantly. The trick lies not in how fast you move, but in how you manipulate the space between. This concept is perfectly compatible with Einstein's theory of general relativity, which allows for space-time to be curved and folded. If space can bend around a star, why not around itself? A wormhole doesn't break the rules, it plays with them creatively. Still, from an outside perspective, it would appear that you've travelled faster than light. Imagine observers on Earth watching you enter a wormhole. To them, you vanish into a strange, warped region of space. Moments later, you appear in a star system thousands of light years away. They would measure the distance and time, compare it to the speed of light, and come to a startling conclusion. You have surpassed the ultimate speed limit. But from your point of view, you've done no such thing. You moved at a perfectly normal pace. The journey was calm, perhaps even serene. There was no rush, no acceleration beyond what your body could handle. You simply stepped through. And yet, this raises profound questions. Questions that stretch far beyond science and into the very nature of causality, time, and reality. Because if wormholes allow you to travel across vast distances faster than light would travel through regular space, then they also potentially allow for travel back in time. Here's how. If one end of the wormhole experiences time differently than the other, perhaps due to gravitational time dilation or rapid motion, then stepping through could mean stepping into the past or future. Let's say one mouth of the wormhole is kept near a massive object like a neutron star, where time flows slowly. The other mouth floats in deep space, where time flows normally. Over time, the two mouths become desynchronized. If you enter the mouth in deep space and exit near the neutron star, you might arrive at an earlier point in time than when you left. In theory, wormholes could become time machines. Again, not by moving faster than light, but by bending the structure of space-time so dramatically that you sidestep time itself. But this brings with it a host of paradoxes. What happens if you go back in time and prevent yourself from entering the wormhole in the first place? Can the universe allow such contradictions? Or does it somehow protect itself from causal loops? Some physicists believe that the laws of quantum mechanics, or cosmic censorship, would prevent time travel via wormholes. Others suggest that the universe would remain self-consistent no matter what, that any action you take in the past was always part of history. Even if time travel remains out of reach, the implications of faster-than-light apparent travel are astonishing. For interstellar exploration, it would be a revolution. Imagine sending a probe through a wormhole and receiving data from the far side of the galaxy in seconds. Or building a network of wormholes, cosmic highways connecting distant star systems, bypassing the need for engines, fuel, or decades-long journeys. Communication, travel, colonization, everything would change. We wouldn't just explore the galaxy, we would live in it. But there are challenges, massive ones. Creating or stabilizing a wormhole requires exotic matter with negative energy density, something we haven't yet been able to generate in useful quantities. The energy required to open a usable wormhole might be enormous, perhaps greater than anything we can currently produce. And there's the constant threat of collapse. Even the tiniest disturbance inside the wormhole could cause it to close, destroying anything inside. There's also the issue of destination. How do you aim a wormhole? Can one end be moved? Can the tunnel be stretched or reshaped? We don't know. Right now, the whole idea remains theoretical, a dazzling possibility drawn from the equations of relativity and quantum physics. Still, the fact that the math works at all is astonishing. That a universe governed by such precise, elegant laws allows for such wild possibilities. That a species made of atoms and stardust can look at the sky, write equations on a chalkboard, and realise, if this is true, then the stars are closer than we ever imagined. So, do you travel faster than light when you enter a wormhole? Not exactly. You travel in a way that light can't, not by outrunning it, but by outsmarting it. By stepping through the hidden folds of space-time that light, bound to its straight-line path, cannot see. It's not speed, it's geometry. It's the cosmic equivalent of walking through a secret door while the rest of the universe plods along the long road. And that perhaps is even more magical. Not because you break the rules, but because you find the hidden passages written into the laws themselves. You've made the leap. You've stepped into a wormhole, travelled through a twisting tunnel of space-time, and now, after a journey unlike any other, you're emerging from the other side. But as you drift toward the exit, as the shimmering corridor begins to widen and the distortions of light and time slowly begin to calm, a single, almost childlike question arises in your mind. Where are you? This is perhaps the most compelling mystery of all, because unlike a spacecraft, which follows a predictable trajectory, or a beam of light that obeys straight lines through vacuum, a wormhole doesn't just take you somewhere, it may take you anywhere. It might even take you elsewhere, to a place so fundamentally different from your point of origin that the only thing left to orient you is wonder. In theory, a wormhole can connect any 2 points in space. Those points could be light years apart. They could be in separate galaxies. They could be on opposite sides of the visible universe. Or they could be within the same solar system, linking 2 remote corners of space like a tunnel under the surface of a vast ocean. The destination depends on the configuration of the wormhole itself, on where its mouths are located, and how its geometry is aligned. But the real fascination lies in this. The other side of the wormhole may not just be another place in our universe. It may be somewhere entirely different. One of the boldest ideas in modern theoretical physics is that of the multiverse. The suggestion that our universe, vast as it is, may be only one of many. A single bubble in an endless sea of universes, each with its own physical laws, its own dimensions, its own histories. If wormholes exist, and if some of them are stable and traversable, they may serve as portals not just between places, but between realities. Step through one, and you might find yourself in a universe where gravity is weaker, where stars burn blue instead of yellow, where life, if it exists, evolved in unimaginable forms. You could exit into a place with no stars at all, just a swirling fog of primordial energy. Or perhaps you arrive on the edge of a black hole orbiting a planet you've never seen, in a sky with moons that change colour every hour. In the infinite landscape of possibility, any of this, and more, is permitted by the mathematics of space-time. But even if you remain within our own universe, the location could still be utterly unfamiliar. You might emerge in a galaxy so far away that its starlight hasn't yet reached Earth. The sky would be a stranger to you. No Orion, no Big Dipper, no Milky Way stretching overhead. You would be in a region of space untouched by our radio waves, undisturbed by our presence. A quiet, ancient corner of the cosmos that has never known life from Earth. And if the wormhole is also a time machine, then the mystery deepens even further. Because now, your destination isn't just a different location in space. It could be a different era in history. You could step into the far future, where humanity has spread across the stars, or vanished entirely. Or into the distant past, where stars were young and galaxies still coalescing from clouds of hydrogen and dust. Perhaps you arrive to find a planet orbiting a sun that hasn't yet formed planets. Or you witness a universe colder, darker, nearing its end. Would you even recognize the cosmos? Would it recognize you? The unsettling beauty of wormholes is that they erase boundaries between here and there, between now and then, between known and unknown. They challenge your ability to orient yourself, to say with confidence where you are. A map becomes meaningless. A clock becomes irrelevant. You are no longer a traveller in space. You are a traveller in reality. And this brings with it another question, one that echoes quietly in the back of the mind. Can you ever return? Wormholes, by their nature, require two ends. If the entrance and exit are stable and connected, it may be possible to go back the way you came. But that depends on many delicate variables. If the wormhole collapses behind you, or if the exotic matter stabilizing it is disrupted, the path could vanish. Your journey may be one way, a door that only opens once. That possibility of permanent displacement adds both awe and melancholy to the experience. To emerge from a wormhole might mean stepping into a new beginning, or being cut off from everything you've ever known. The stars you grew up under, the people you left behind, the earth itself may now exist only in memory. And yet, there's something deeply human about that risk. After all, the earliest explorers of our world also stepped into the unknown. They sailed across oceans without knowing what lay beyond the horizon. Some found new lands, others found nothing. But all of them shared that same quiet courage, the willingness to be lost in the hope of discovering something greater. In the same way, stepping out of a wormhole might feel like standing on the shore of a new universe, a frontier beyond imagining. Your surroundings may be silent, alien, or profoundly beautiful. You may be alone, or you may not. You may find remnants of other travellers, ancient civilizations, or even intelligent beings watching you from afar. Or perhaps nothing at all, just space. Vast, empty waiting. And in that moment, as you take your first breath on the far side, you begin to realize that the destination itself was never the point. It was the act of reaching it, the crossing, the leap, the journey through the impossible, that changed you. You're no longer bound by the slow walk of photons or the patience of rocket engines. You've stepped beyond the limits of classical thought into a universe that is deeper, richer, more mysterious than anyone ever imagined. So where would you come out? Anywhere, everywhere, nowhere. And that answer, as strange as it is, might be the most beautiful one of all. There's something profoundly unsettling, yet endlessly fascinating, about the idea of meeting yourself. Not in a mirror, not in a dream, but in reality. A flesh and blood version of you who has made different choices, lived in a different time, aged differently, suffered differently, rejoiced at things you never experienced. Someone who is you, and not you. And within the strange physics of wormholes, this chilling encounter might not be impossible. It might even be inevitable. At first glance, wormholes appear to be simple cosmic shortcuts, tunnels linking distant points in space. But when time becomes part of the equation, the picture grows infinitely more complex. According to the laws of general relativity, space and time are not separate entities. They form a single, unified structure known as space-time. If a wormhole can connect 2 points in space, it can also, under the right conditions, connect 2 points in time. The consequences of this are staggering. Let's imagine a stable wormhole with 2 mouths, one fixed near the Earth, and the other aboard a spaceship travelling at relativistic speeds, close to the speed of light. As Einstein showed, time passes more slowly for objects in motion compared to those at rest. If the spaceship moves fast enough and then returns to its starting point, the 2 mouths of the wormhole will now exist at different moments in time. In effect, one becomes the past, and the other becomes the future. Step into the future mouth, and you emerge in the past. Step back, and you return to your own present. It sounds like science fiction, but the math supports it. And once time travel enters the picture, an avalanche of philosophical and physical questions follows. Because if you can travel into the past, could you meet yourself? Not just a memory, not a ghost or dream, but the actual you, walking, breathing, thinking in real time. A version of yourself from a moment earlier in life, maybe from 5 minutes ago, maybe from 5 years ago, maybe from childhood. The thought is both thrilling and terrifying. What would you say to yourself? Would you offer warnings, advice? Would your past self recognize you? Would they trust you? Or would it feel like staring into the face of a stranger wearing your skin? Physicists refer to these possibilities as closed time-like curves, loops in time where events can circle back on themselves. In such a loop, cause and effect can become jumbled. You might give your younger self a piece of information they later pass to you, creating a self-contained paradox with no clear origin. This is known as a bootstrap paradox, an object or fact that exists without ever being created, looping endlessly through time. For example, Imagine you hand your younger self a scientific formula. That version of you goes on to publish it. The world applauds your genius. Years later, you step back in time and give that formula to your younger self again. Where did the formula actually come from? From you, but only because it already existed. It has no true beginning, just an endless loop of information sustained by the wormhole. This kind of paradox unsettles physicists because it seems to defy the most basic logic. Effects should follow causes, not precede them. Events should have origins. But in a universe with wormholes and time loops, these principles begin to fray at the edges. Reality becomes a spiral rather than a line. But what about the emotional impact of meeting yourself? Seeing your past self might awaken feelings of grief, joy, or regret. You may be reminded of who you once were, of the hopes and fears that shaped you. Perhaps your younger self is more optimistic, more trusting, or perhaps they're wounded in ways you've since healed. And what would it mean for that younger version of you to see who you have become? Would they be proud or disappointed? Then there's the even stranger possibility. What if your future self appears to you? One day, without warning, you encounter someone who looks older, wiser, quieter. They move like you, speak like you, know things they shouldn't. And then they tell you, I am you, from 20 years in the future. I've come through a wormhole. Would you believe them? Would you ask about your future? Try to change it, or would you recoil from the responsibility of knowing too much? Because knowledge of the future is a heavy burden. It could rob you of spontaneity, freedom, even hope. What if you're told that a certain choice leads to ruin, or that a certain person will leave your life forever? In such moments, wormholes stop being scientific curiosities. They become moral mirrors. They force you to confront who you are, who you were, and who you might become. They make time deeply personal. Yet some physicists believe that paradoxes like these may be self-resolving. This is the idea behind the Novikov self-consistency principle, which suggests that events in space-time are constrained in such a way that paradoxes simply can't happen. In other words, if you go back in time, you might want to change the past, but the universe will subtly prevent it. Your actions will end up reinforcing the timeline rather than disrupting it. You might try to stop a disaster, only to find that your attempt was what caused it in the first place. You might attempt to save someone, only to realize that your very presence was part of the events leading to their fate. Time in this model is like a river with strong currents. You can splash around, maybe cause a few ripples, but you can't stop it from flowing toward its destination. This idea is comforting in a way. It suggests the universe protects itself. But it also suggests that meeting your past or future self may not be something you choose. It may be something that must happen, part of a preordained loop already embedded in the structure of time. And yet, there are other models, many worlds interpretations, quantum branching theories, that allow for a more chaotic vision. In these models, entering a wormhole and meeting yourself might trigger a split in the timeline, creating a new parallel universe, where the consequences of your encounter ripple outward freely, independent of your original path. In that universe, the younger version of you may make different choices. Your future self might become someone else entirely. The timeline fractures. A new story begins. But in all these possibilities, one thing is clear. Meeting yourself through a wormhole would be more than an encounter. It would be a revelation. A moment that defies logic, bends identity, and rewrites the narrative of your life. Because to meet yourself is to face a mirror that doesn't lie. A mirror that shows you the full weight of your decisions, your regrets, your dreams. A mirror that asks not just, what would you do differently? But who are you really? And once you've looked into that mirror, into your own eyes from another time, you may never see yourself the same way again. The stars may inspire wonder, but it's human imagination that dares to turn wonder into questions, and questions into science. Among those brave enough to chase the universe's deepest mysteries are the scientists who look at the cold silence of space and ask, could we ever cross it in an instant? Could wormholes be real? At the heart of this pursuit is a blend of bold theory and meticulous mathematics. NASA, alongside theoretical physicists across the globe, has not dismissed wormholes as mere science fiction. In fact, they've explored the possibility that these cosmic shortcuts could one day be part of our reality, not just as speculative curiosities, but as potential tools for interstellar travel. Though we are far from building one, the steps we've taken in understanding the science behind them are astonishing. One of the earliest and most influential contributors to the study of traversable wormholes was Kip Thorne, a Nobel Prize-winning physicist, and one of the minds behind the gravitational wave breakthrough. In 1988, Thorne, along with his graduate student Michael Morris and physicist Ulvi Yurtsever, published a groundbreaking paper titled Wormholes, Time Machines, and the Weak Energy Condition. This wasn't just an abstract exploration, it laid out in detail the physical conditions under which a wormhole could be traversable, without turning its traveller into cosmic spaghetti. Their work showed that if exotic matter, material with negative energy density, could be used to stabilise the throat of a wormhole, it might be possible to keep it open long enough for a human being, or even a spacecraft, to pass through. Importantly, they didn't violate Einstein's equations. They worked within the framework of general relativity, twisting and stretching the math to discover how such an object might exist within the known laws of physics. Their study didn't offer blueprints for building a wormhole, but it made one thing clear. The laws of physics do not forbid them. That alone was revolutionary. A possibility was born, not certainty, but a door cracked open. NASA, ever attentive to the fringes of plausible science, took notice. Through its Breakthrough Propulsion Physics project, initiated in the late 1990s, NASA began to investigate concepts that once belonged strictly to science fiction. Warp drives, quantum tunneling, and yes, wormholes. The idea was not to claim that these things could be built tomorrow, but to ask, what would it take? What gaps in our knowledge must be filled to even begin designing such technologies? Under this initiative, physicists like Harold "Sonny" White explored the mathematics of space-time manipulation, particularly in relation to the Alcubierre drive, a theoretical method of faster-than-light travel that contracts space in front of a ship and expands it behind. This idea, while different from wormholes, is mathematically related. Both rely on the manipulation of space-time itself, and both require exotic matter or negative energy to function. White and his team at NASA's EagleWorks laboratory even designed tiny scale experiments to detect fluctuations in the structure of space-time. Early, delicate steps toward understanding how space might be shaped, stretched, or tunneled through. Though these experiments haven't yet led to any breakthroughs, they show a quiet commitment within the scientific community to test even the most radical ideas, provided they don't violate known laws. Meanwhile, the realm of computer simulations and high-level mathematics continues to play a key role in wormhole research. Supercomputers can now model the extreme gravitational environments where wormholes might exist, around black holes, in the chaotic moments after the Big Bang, or in the fabric of quantum foam, where tiny wormholes may flicker in and out of existence at subatomic scales. Theoretical physicists also continue to search for connections between wormholes and quantum mechanics. One of the most intriguing ideas to emerge in recent years is known as EREPR, proposed by physicists Leonard Susskind and Juan Maldacena. This theory suggests a deep link between Einstein-Rosen bridges, wormholes, and quantum entanglement, Einstein-Podolsky-Rosen pairs. In other words, entangled particles may be connected by tiny non-traversable wormholes, implying that space-time itself is woven from these quantum connections. If true, this idea could provide a bridge between the two great pillars of modern physics, general relativity and quantum mechanics. And if wormholes are built into the very foundation of space-time, then perhaps, just perhaps, we are already surrounded by their invisible structure, too small to see, too brief to detect, but essential to everything. The search for wormholes has also received an unexpected boost from popular culture, particularly from films and literature that treat the subject with a surprising level of scientific accuracy. When Christopher Nolan made Interstellar, he turned to Kip Thorne to ensure that the wormhole depicted in the film was based on actual equations. The visuals created for the movie's black hole, Gargantua, were so detailed and accurate that they resulted in new scientific insights into how light bends near such objects. In this way, art and science dance together, bringing the idea of wormholes to a global audience while inspiring real research. But despite all this progress, enormous challenges remain. First, there's the exotic matter problem. While hints of negative energy appear in quantum physics, such as in the Casimir effect, we have yet to isolate or produce it in meaningful quantities. And even if we could, we would need vast amounts to stabilize a wormhole large enough for travel. Second, we still have no observational evidence that wormholes exist at all. We've never seen one, never detected a signature that couldn't be explained by something else. Some researchers have proposed methods of searching for wormholes using gravitational lensing or radio wave interference. But so far, the universe has been quiet. And then there's the engineering problem. Even if wormholes exist in the wild, how would we capture one? How would we transport a wormhole mouth from one part of space to another? How do you contain something that is, in essence, a hole in the fabric of reality itself? These questions remain unanswered. But if science has taught us anything, it's that today's impossibilities often become tomorrow's achievements. The airplane was once a dream. The moon was once unreachable. Quantum entanglement was once absurd. And now, scientists manipulate entangled particles in laboratories and send probes beyond Pluto. Wormholes may not be built or discovered in our lifetime, but the foundation is being laid, quietly, patiently, methodically, and in the halls of NASA, in university physics departments, in observatories watching the stars flicker, people are still asking, what if? What if the universe hides tunnels through space-time? What if the distances that separate us from other worlds are not as absolute as they seem? What if the future of exploration isn't just out there, but just one wormhole away? In that question lies the hope not only of travel, but of transformation. A future in which space and time themselves become navigable, where the stars are not just distant lights, but destinations. The universe we see, the stars, planets, galaxies, is vast beyond imagining, but it might be just one layer in an even grander cosmic tapestry. Modern theoretical physics suggests that our universe could be one among many, a multiverse, an infinite or near infinite collection of universes, each with its own unique physical laws, constants, and histories. If wormholes exist, they might not only connect distant regions of our own universe, but also bridge entirely different universes within this multiverse. Imagine, for a moment, stepping through a doorway that doesn't just transport you across space or time, but into a place where the very fabric of reality is different. Here, the constants of physics, the speed of light, the strength of gravity, the nature of particles, might shift in ways subtle or radical. In one universe, stars might never form. In another, life might be based not on carbon, but on entirely unknown chemistry. The idea that wormholes could link these universes is both thrilling and humbling. Such connections would be cosmic gateways, portals into realms where the familiar fades and the extraordinary begins. Travelling through one would challenge every assumption you hold about reality. Colours might appear unfamiliar, sounds may behave oddly, and time could flow in unpredictable ways. It's a realm of endless possibility, and naturally, endless danger. If the multiverse is real, and wormholes serve as inter-universal bridges, it raises profound questions. Would you ever be able to return to your original universe? Could you communicate between these vastly different realities? And perhaps most hauntingly, if you crossed into another universe, would you remain yourself? Or would you become something else entirely? The possibility that wormholes connect to multiverses adds a cosmic dimension to the old human quest for exploration and understanding. It extends our reach from the stars to the very nature of existence, asking us to consider that reality might be layered, complex, and infinitely varied. Yet this grand vision comes with its own risks and mysteries. Wormholes linking universes might be highly unstable. The energy differences between universes could cause the tunnel to collapse or become a one-way passage. And entering an alien universe might mean encountering unknown physical dangers, energies or forces we cannot predict or survive. Still, for all these unknowns, the possibility itself stretches the imagination. It invites us to see the universe not as a solitary island, but as part of an archipelago of realities, each distinct, each mysterious, and perhaps each waiting to be explored. As we ponder these possibilities, we must also confront the realities closer to home. Wormholes, even if traversable, are not gentle passages. They exist in extremes. The forces at play within them are immense, often violent. Radiation levels near a wormhole's throat could be extraordinarily high. The bending of space-time can trap particles and photons, creating intense energetic fields. Any traveller would need protection far beyond what current technology can offer. Without shielding, radiation could damage cells, alter DNA, or worse. Then there's the matter of tidal forces, the differential gravitational pull on different parts of an object. Near a wormhole's narrowest point, these forces could stretch and compress anything passing through, an effect known as spaghettification. Imagine your body being pulled apart lengthwise, as gravity on one end of you is stronger than on the other. Surviving such a journey would require extraordinary engineering, or perhaps the intervention of exotic matter, stabilizing the wormhole's geometry. Moreover, the tunnel itself might be chaotic. Quantum fluctuations and instabilities could cause the wormhole to fluctuate in size and shape unpredictably. This could lead to sudden collapses or dangerous distortions mid-journey. Even a brief closure while inside would be catastrophic. The mental and psychological toll of travelling through such a passage should not be underestimated. The distortions of light, space, and time could confuse senses, distort perception, and cause disorientation or hallucinations. The experience might feel like slipping into a dream or a nightmare. Despite these dangers, the image of drifting peacefully through the stars remains compelling. Imagine, after enduring the initial turbulence, that the wormhole stabilizes around you. The chaotic distortions fade. You find yourself in a quiet corridor, bathed in soft, diffuse light, neither day nor night, but an eternal twilight. Time seems to slow. The vast distances of the cosmos collapse into a gentle flow. In that silence, you might sense the universe's heartbeat, the subtle pulse of space-time itself, the fragile beauty of cosmic geometry, the unseen threads that weave the stars together. And as you glide through this serene passage, you realize that the journey is not just physical. It's spiritual, a moment of quiet awe in the vastness. A reminder that, for all its dangers and mysteries, the universe is a place of wonder. As the tunnel begins to widen and the exit approaches, you prepare to step out, back into the light, into a new region of space, or perhaps into a new universe. The unknown awaits. But in this moment, you are suspended between worlds, embraced by the silence and the infinite calm of the cosmic depths. The journey through a wormhole is a passage not just through space or time, but through mystery itself. And in that quiet, profound crossing, you find a deeper connection to the cosmos, a reminder that even in the vast darkness, there is light.